Hi everyone. In the last class we have discussed about spectrum of an element in a Banach algebra, and we have shown that spectrum is a non-empty compact subset of C for a given element in a Banach algebra. Today we will continue to discuss some more important properties of the spectrum. So let us start with a unital Banach algebra. Let A be a unital Banach algebra and A, B are two elements in A. If norm of AB is strictly less than 1 and norm of BA is also strictly less than 1, then we can say that 1 minus AB inverse we can express in terms of 1 minus BA inverse, that is 1 plus 1 minus BA inverse AB. Similarly, 1 minus BA inverse also we can express in this way. So let us try to look at the idea. So norm AB norm AB less than 1 implies 1 minus AB is invertible, and 1 minus AB inverse we can write this as summation n equal to 0 to infinity AB all power n. So this is nothing but 1 plus AB plus AB, so that is AB square plus AB, so on like this. Okay. Now we want to express this in terms of BA, so we can multiply this equation with B from the left hand side and A from the right hand side. So this implies B into 1 minus AB inverse A. This is nothing but the first term is BA, second term is BA, the third term is B, AB, A plus B, AB, A, and so on. Like this we get. Now we want to write this in terms of BA. So this is BA plus BA square plus this is BA cube, so on. This is BA power 4, and this is nothing but the series summation n equal to 1 to infinity BA power n. Now we know that norm BA is less than 1, so this we can add 1 and subtract 1, so this is summation n equal to 0 to infinity BA power n minus 1. So this is nothing but 1 minus BA whole inverse minus 1. So therefore we can say that 1 minus BA inverse can be obtained as 1 plus B into 1 minus AB inverse A. So we can express 1 minus BA whole inverse in terms of 1 minus AB inverse in this way. Now similarly the other way also we can write down 1 minus AB. Similarly 1 minus AB inverse we can write as 1 plus 1 minus BA inverse. This is B, this is A, and this is the same trick we can use. Okay, this is by using the Neumann series. Now without using also we can prove this result. Let me write as proposition let A, B be elements of A, where A is a unital Banach algebra. Unital Banach algebra. Then we can say that 1 minus AB is invertible if and only if 1 minus BA inverse BA is invertible. So earlier we assumed that condition norm AB less than 1 and norm BA less than 1, and there actually 1 minus AB invertible we have assumed, and 1 minus BA is also we have assumed 1 minus BA is also invertible. Okay, so let us try to look at the proof. So assume that 1 minus AB is invertible. Then following the earlier method, we can actually write down the inverse for 1 minus BA. So let us write C as 1 plus B into 1 minus AB inverse into A. Then we want to show that C is the inverse of 1 minus BA. So claim C is the inverse of 1 minus BA. So let us consider 1 minus BA into C. This is C minus BAC, but C is nothing but 1 plus B, 1 minus AB inverse into A minus BA into C, that is first term is minus BA minus BAB 1 minus AB whole inverse A. So this we can again, if you look at the terms here, let us try to take this term common here. So we can write this as 1 minus BA plus B minus BAB multiplied by 1 minus AB inverse into A. So again we can write this as 1 minus BA plus, we can take B in this term common from the left hand side. So you will get B into 1 minus AB, 1 minus AB inverse A. So you will get 1 minus BA plus BA, so that is 1. Similarly, we can show that, check that C into 1 minus BA is exactly 1. So from these two arguments we can conclude that C is the inverse of 1 minus BA. And the other implication also we can show the same, following the same method. So whenever we assume that 1 minus BA is invertible, we can show that 1 minus AB is also invertible. So this completes the proof of this result. Now as a corollary, so let us take lambda in C, lambda non-zero, then we can show that lambda into 1 minus AB is invertible if and only lambda into 1 minus BA is invertible. That means, or we can say that spectrum of AB minus BA, spectrum of AB minus 0 is nothing but spectrum of BA minus 0. This can be proved using the same trick. So now lambda, so idea is the simple. So lambda into 1 minus AB you can write as lambda into 1 minus AB by lambda. Now we know that this is invertible if and only this is invertible, because lambda is non-zero. So now use the earlier method to conclude the result. Okay, so now has particular cases. So let us take S and T or T are two elements of B of H, where H is a Hilbert space. Then we can say that spectrum of ST minus 0 is spectrum of TS minus 0. Again, in particular, spectrum of T star T minus 0 is nothing but spectrum of T star minus 0. This is again a particular case. Okay, so this is about the spectrum of AB in terms of spectrum of BA. Next, we want to look at the following information about spectrum of an element in a Banach algebra. Now, we can easily show that if A is invertible, then spectrum of A inverse is nothing but 1 by lambda. Lambda is coming from spectrum of A. The second one, if lambda is a complex number, then spectrum of A plus lambda into 1 can be shown as mu plus lambda, where mu is coming from spectrum of A. We can also easily show that spectrum of A square is set of all lambda square, lambda in the spectrum of A, which can be written as spectrum of A whole square. This can be proved in a easy way by using the earlier tricks. Okay, now we can ask the question, suppose if P is a polynomial, let P of Z is alpha naught plus alpha 1 Z plus alpha 2 Z square, so on alpha n Zn, where this alpha j is a complex number, alpha n non-zero. Then we can write as P of A plus alpha 1 A, alpha 2 A square, so on alpha n A power n. Now we can ask the question, what is the relation between spectrum of PA in terms of spectrum of A? And spectrum of A. So we will answer this question now. This result is known as the spectral mapping theorem. Okay, let A be a unital Banach algebra and A is an element of A. If P is a polynomial with complex coefficients, then we can say that spectrum of P of A is nothing but P of spectrum of A. This means that this is set of all P lambda, where lambda is an element of spectrum of A. So this is known as the spectral mapping theorem. When P of z equal to z square, we get the earlier question that we have asked. Spectrum of A square is nothing but spectrum of A whole square. If P is a linear polynomial, we get the second condition. Spectrum of A plus lambda 1 is mu plus lambda. Mu is coming from spectrum of A. Okay, so to prove this result, we need one important lemma. So let us write as a lemma that lambda 1, lambda 2, so on, lambda n are complex numbers. Then we can say that the product pi a minus lambda j into 1, j equal to 1 to n, is invertible if and only if a minus lambda j into 1 is invertible for all j 1 to n. Okay, so let us try to look at the proof. So if a minus lambda j 1 is invertible for every j, we can easily get the inverse of this one. So this one is trivial. Now let us prove the other way. So let us take let S be the inverse of this product a minus lambda j1, where j equal to 1 to n. Now let us fix j in this set 1, 2, 3, so on n. We want to show that a minus lambda j into 1 is invertible. So let us look at B as the product summation k equal to 1 to m a minus lambda k into 1, but k not equal to the j that we have fixed. Now it is easy to check that S into B minus a minus lambda j into 1, this is nothing but S into the product j equal to 1 to n, k equal to 1 to n, a minus lambda k into 1. So this is nothing but 1. Okay, so this is, we are using the fact that a minus lambda j 1 in, a minus lambda j commutes with a minus lambda k for every k. So this implies SB is a left inverse of a minus lambda j into 1. Now on the other hand, we can also check by using the commutativity of a minus lambda j with a minus lambda k. We can show that a minus lambda j into 1 multiplied by b into s is again 1. So that means this operator, sorry, this element bs, so that means bs is a right inverse of a minus lambda j into 1. So a minus lambda j into 1 has both a left inverse and a right inverse. Hence we can conclude that a minus lambda j into 1 is invertible, and its inverse is nothing but bs, and that is equal to sb. So therefore we can conclude that a minus lambda j is invertible. Okay, and we have fixed j, one of the j's. So this is true for all j. So this completes the proof of the lemma. Now let us try to look at the spectral mapping theorem. Okay, so we want to show P of sigma A is contained in sigma of PA, and so first let us try to look at this part, then we can show the other way inclusion also. So let us take lambda in the spectrum of A. Okay, then we can write so we have Pz minus P lambda can be written as C times Z minus lambda multiplied by Z minus lambda 2, so on Z minus lambda n. So this is a polynomial, we can write this way using the fundamental theorem of algebra. Okay, so where C is non-zero and lambda 2, lambda 3, so on lambda n are complex numbers. Okay, then we have P of A minus P lambda C times A minus lambda, A minus lambda 2, so on A minus lambda n. So let us take lambda 1 as lambda, then we can say that PA minus P lambda is nothing but C times product A minus lambda J1 j equal to 1 to n. So here you can write ones all the places or no problem. Now lambda 1 is element in the spectrum of A, implies A minus lambda 1 into 1 is not invertible. So this implies PA minus P lambda is not invertible. This here we can write 1. So here 1. This is not invertible in A. So this implies that P lambda is in spectrum of. So we have taken lambda in the spectrum of A and we have shown that P lambda 1 is in spectrum of P of A. So this spectrum of, so we have shown that P of spectrum of A is contained in spectrum of P of A. Now let us look at the other inclusion. So we want to show spectrum of PA is contained in P of spectrum of A. This is what we want to show. Let us take mu from spectrum of P of A. We want to show that mu is nothing but P lambda for lambda in, for some lambda in spectrum of A. So consider Pz minus mu times 1. We can write this as C times Z minus beta 1, Z minus beta 2, so on for some complex numbers. C non-zero, beta 1, beta 2, so on beta n. Okay, now P of A minus mu times 1, this is C times A minus beta 1 into 1, A minus beta 2 into 1, so on A minus beta n into 1. Okay, now the left hand side is not invertible. This is not invertible. So by lemma we can say that, so by the lemma a minus beta j into 1 is not invertible for some j in this set 1, 2, 3, so on n. And we know that also we know that p of beta j minus mu is 0, or mu is nothing but p of beta j. Now beta j is coming from spectrum of A, so because of this one, so this is in P of spectrum of A. So we have taken mu from spectrum of P of A, and we have shown that it is in P of spectrum of A. Hence we can conclude that this is true. Now from these two arguments we can conclude that spectrum of P of A is exactly P of spectrum of A. So this is the spectral mapping theorem, also known as a polynomial version of spectral mapping theorem. Okay, so let us look at one example related to this one. Let A be a unital Banach algebra and A is an element of A such that A square equal to A. Then we can conclude that spectrum of A is part of this set 0, 1. It may be 0, it may be 1, or it may be equal to spectrum of, it may be equal to the whole set 0, 1. Okay, so let us define, to prove this, let us define P of z as z square minus z. Then we have P of A, that is A square minus A. We know that A square equal to A, this is 0. So by the spectral mapping theorem, so we have spectrum of P of A, or we can say that P of spectrum of A is spectrum of P of A, but this is spectrum of the element 0, this is 0. That means if lambda is in spectrum of A, then P of lambda is 0, or we can say that lambda square is equal to lambda, that is lambda is 0 or 1. So we can say that spectrum of A is contained in the set 0, 1. So this is one of the examples for the spectral mapping theorem. Okay, next we want to look at something, some information about the spectrum again. So let us recall from the earlier lecture. So we have seen examples. If you take A as 0, 1, 0, 0, so we have shown that spectrum of A is the singleton set 0. And if you look at norm of A, so we can easily look at norm of A is nothing but square root of A star A but A star A is nothing but 0 1 0 0 0 1. So we can easily 0 1 0 0 multiplied by we want to look at A star A. Zero one zero zero 0 1 0 0, so we can get 0 0 0 1. Okay, so this is we will get, and norm of this is 1. It's a diagonal operator whose diagonal entries are 0 and 1. So norm of this operator is maximum of modulus of the diagonal entries. So we can get this as 1. The spectrum is 0. We know that spectrum of A is part of the closed ball centered at 0 with, so this is okay, but so here spectrum is single point, whereas if you look at the ball centered at 0 with radius 1, you will get the closed unit disk. Now let us look at one more example. So let us take A as C dash 0 1. You take, when f is in A, define norm f as subnorm of f plus subnorm of f dash. So let us take a function f of f naught of t equal to t for every t in 0 1. We know that spectrum of f naught, by the earlier calculation, this is range of f naught. The spectrum is, so we get spectrum as this one, but norm of f is nothing but subnorm of f, that is 1, plus f dash is 1, so this is 2. So that means we are looking at a ball centered at 2 and centered at 0 with radius 2. So this is included in very bigger ball. Now instead of this, what we can do is, let us take spectrum of A. Now look at the distance between 0 and the maximum point of the spectrum, which is far away from the point 0. So look at the maximum distance. Now look at the ball centered at 0 with this as the radius. So we can say that spectrum of A is contained in ball centered at 0 with some r, where r is less than or equal to norm A, but we can define, so we can write this is r of A, which depends on A. So we call this is r of A, ball centered at 0 with radius r of A. So this is called the spectral radius of A. So for A in A, define r of A as the maximum distance between 0 and all the spectral points of A. So this is supremum mod lambda, where lambda is coming from spectrum of A. So this is known as the spectral radius of, it is the radius of the smallest ball containing the spectrum of A. So by the definition, so R of A, so spectrum of A is contained in the ball centered at 0 with radius norm A and closure. So this implies that spectral radius of A is always less than or equal to norm A. Now if you look at the earlier examples, let us look back here. The spectrum is 0, so spectral radius in this case is 0 and norm is 1, so this is less than norm of A. And the second example, if we observe, the spectral radius of F naught is 1, which is less than norm of F. So in general, spectral radius and norm need not be same, but in particular cases, if I take A to be C of K, where K is compact Hausdorff space, so if we take any element F in A, then we know that spectrum of F is nothing but range of F. And spectral radius by definition, this is supremum of mod lambda, where lambda is coming from range of F. So this is exactly supremum of mod F of t, where t is coming from K, and this is nothing but. So in this case, the spectral radius and norm of element are same, and we can later show that if you have any commutative Banach algebra, commutative C star algebra, this is the case. So we will be looking at a later stage, and in fact we can show that if T is a normal element, normal operator on a Hilbert space, then also we can show that spectral radius and norm are same. To show that, we need some more information about operators, so we will postpone that to a later stage. Okay, so this is the spectral radius, and some cases spectral radius is very smaller than the norm of the operator. We have already seen a few such examples. Okay, now the question we can ask is the following: how to compute the spectral radius? So one way is to look at the spectrum and use the definition of the spectral radius of an element. The other way is that we have to find a formula. We will be proving in the next class that which we call as the spectral radius formula. So I will stop here. Thank you very much.